So yes, some of them say that there's a cycling universe, and so the Big Bang is an event when space gets very hot and very dense and filled with particles. For nearly 60 years, the Big Bang has reigned supreme as our most successful theory for explaining our cosmic origins, beginning from a hot dense matter and radiation-rich state. The universe has expanded, cooled, and gravitated ever since. As it evolved, it formed protons and neutrons, the first light elements, stable atoms, and eventually stars, galaxies, planets, and complex chemistry capable of giving rise to life. Some 13.8 billion years after it all began, here we are, observing the still expanding universe and working to figure out exactly where it all came from and how it came to be the way it is today. However, the deeper we dig, the more the Big Bang picture breaks. The universe arises from nothing, and that puzzle is why many scientists, including the famous physicist Brian Cox, strongly reject the Big Bang theory. The problem gets more intense as the most powerful space telescope ever, the James Webb Space Telescope, obtains some very strong evidence demonstrating that the Big Bang wasn't truly the start of it all. That raises the question, what existed before the Big Bang? And if the Big Bang wasn't the beginning, well, what was? Stay tuned today as we shed some new light on the origin of the universe in today's episode of Mega Entertainment. The first time the phrase the Big Bang was uttered was over 20 years after the idea was first described. Ironically, the term itself comes from one of theory's greatest detractors, Fred Hoyle, who was such a staunch advocate of the rival idea of a steady-state cosmology. In 1949, he appeared on BBC Radio and advocated for what he called the perfect cosmological principle, the notion that the universe was homogeneous in both space and time. He went on to deride the opposing notion as a hypothesis that all matter of the universe was created in one Big Bang at a particular time in the remote past, which he then called irrational and claimed to be outside science. But I'm afraid I don't really believe in the Big Bang. But the idea in its original form wasn't simply that all the universe's matter was created in one moment in the finite past. That notion derided by Hoyle had already evolved from its original meaning. Originally, the idea was that the universe itself, not just the matter within it, had emerged from a state of non-being in the finite past. And that idea, as wild as it sounds, was an inevitable but difficult to accept consequence of the new theory of gravity put forth by Einstein way back in 1915, his theory of general relativity. When Einstein first cooked up the general theory of relativity, our concept of gravity forever shifted from the prevailing notion of Newtonian gravity. Under Newton's laws, the way that gravitation worked was that any and all masses in the universe exerted a force on one another instantaneously across space, in direct proportion to the product of their masses, and inversely proportional to the square of the distance between them. But in the aftermath of his discovery of special relativity, Einstein and many others quickly recognized that there was no such thing as a universally applicable definition of what distance was or even what instantaneously meant with respect to two different locations. With the introduction of Einstein's relativity, the notion that observers in different frames of reference would all have their own unique equally valid perspectives on what distances between objects were and how the passage of time worked. It was only almost immediate that the previous absolute concepts of space and time were woven together into a single fabric, space-time. All objects in the universe moved through this fabric, and the task for a novel theory of gravity would be to explain how not just masses, but all forms of energy shape this fabric that underpinned the universe itself. Although the laws that governed how gravitation worked in our universe were put forth in 1915, the critical information about how our universe was structured had not yet come in. While some astronomers favored the notion that many objects in the sky were actually island universes that were located well outside the Milky Way galaxy, most astronomers at the time thought that the Milky Way galaxy represented the full extent of the universe. Einstein sided with this latter view, thinking the universe was static and eternal, added a special type of fudge factor into his equations, a cosmological constant. Although it was mathematically permissible to make this addition, the reason Einstein did so was because without one, the laws of general relativity would ensure that a universe that was evenly uniformly distributed with matter, which ours seemed to be, would be unstable against gravitational collapse. In fact, it was very easy to demonstrate that any initially uniform distribution of motionless matter, regardless of shape or size, would inevitably collapse into a singular state under its own gravitational pull. By introducing this extra term of cosmological constant, Einstein could tune it so that it would balance out the inward pull of gravity by proverbially pushing the universe out with an equal and opposing action. But the two developments, one theoretical and one observational, would quickly change this early story that Einstein and others had told themselves. In 1922, Alexander Friedmann worked out fully the equations that governed a universe that was isotropically the same in all directions and homogeneously the same in all directions, filled with any type of matter, radiation, or other forms of energy. He found that such a universe would never remain static, not even in the presence of a cosmological constant, and that it must either expand or contract depending on the specifics of its initial conditions. In 1923, Edwin Hubble became the first to determine that the spiral nebulae in our skies were not contained within the Milky Way galaxy, but rather were located many times farther away than any objects that comprised our home galaxy. The spirals and ellipticals found throughout the universe were, in fact, their own island universes, now known as galaxies. And moreover, as had been previously observed by Vesto Slipher, the vast majority of them appeared to be moving away from us at remarkable speeds. In 1927, Georges Lemaitre became the first person to put these pieces of information together, recognizing that the universe today is expanding. And if things are getting farther apart and less dense today, then they must have been closer together and denser in the past. Extrapolating this back all the way to its logical conclusion, he deduced that the universe must have expanded to its present state from a single point of origin, which he called either the cosmic egg or the primeval atom. This was the original notion of what would grow into the modern-day theory of the Big Bang, the idea that the universe had a beginning or a day without yesterday. It was not, however, generally accepted for some time. Lemaitre originally sent his ideas to Einstein, who infamously dismissed Lemaitre's work by responding, "Your calculations are correct, but your physics is abominable." Despite the resistance to his ideas, however, Lemaitre would be vindicated by further observations of the universe. Many more galaxies would have their distances and redshifts measured, leading to the overwhelming conclusion that the universe was and still is expanding equally and uniformly in all directions on large cosmic scales. In the 1930s, Einstein conceded, referring to his introduction of the COSM, a logical constant in an attempt to keep the universe static, as his greatest blunder. However, the next great development in the formulating of what we know as the Big Bang wouldn't come until the 1940s when George Gamow, perhaps not so coincidentally an advisee of Alexander Friedmann, came along in a remarkable leap forward. He recognized that the universe was not only full of matter but also radiation, and that radiation evolved somewhat differently from matter in an expanding universe. Gamow leveraged this fact to make three great generic predictions about the young universe. 1. At some point, the universe's radiation was hot enough so that every neutral atom would have been ionized by a quantum of radiation, and that this leftover bath of radiation should still persist today at only a few degrees above absolute zero. 2. At some even earlier point, it would have been too hot to even form stable atomic nuclei, and so an earlier stage of nuclear fusion should have occurred where an initial mix of protons and neutrons should have fused together to create an initial set of atomic nuclei, an abundance of elements that predates the formation of atoms. 3. Finally, this means that there would be some point in the universe's history after atoms had formed where gravitation pulled this matter together into clumps, leading to the formation of stars and galaxies for the first time. These three major points, along with the already observed expansion of the universe, form what we know today as the four cornerstones of the Big Bang. Although one was still free to extrapolate the universe back to an arbitrarily small dense state, even to a singularity if you're daring enough to do so, that was no longer the part of the Big Bang theory that had any predictive power to it. Instead, it was the emergence of the universe from a hot dense state that led to our concrete predictions about the universe. Over the 1960s and 1970s, as well as ever since, a combination of observational and theoretical advances unequivocally demonstrated the success of the Big Bang in describing our universe and predicting its properties. 1. The discovery of the cosmic microwave background and the subsequent measurement of its temperature and the blackbody nature of its spectrum eliminated alternate theories such as the steady-state model. 2. The measured abundances of the light elements throughout the universe verified the predictions of Big Bang nucleosynthesis, while also demonstrating the need for fusion in stars to provide the heavy elements in our cosmos. 3. The farther away we look in space, the less grown-up and evolved galaxies and stellar populations appear to be, while the largest scale structures like galaxy groups and clusters are less rich and abundant the farther back we look. The Big Bang is verified by our observations, accurately and precisely describing the emergence of our universe as we see it from hot, dense, almost perfectly uniform early stages. But what about the beginning of time? What about the original idea of a singularity and an arbitrarily hot, dense state from which space and time themselves could have first emerged? That's a different conversation today than it was back in the 1970s and earlier. Back then, we knew that we could extrapolate the hot Big Bang back in time, back to the first fraction of a second of the observable universe's history. Between what we could learn from particle colliders and what we could observe in the deepest depths of space, we had lots of evidence that this picture accurately described our universe. But at the absolute earliest times, this picture breaks down. There was a new idea proposed and developed in the 1980s known as cosmological inflation that made a slew of predictions that contrasted with those that arose from the idea of a singularity at the start of the hot Big Bang. In particular, inflation predicted the following points. 1. A curvature for the universe that was indistinguishable from flat to the level of between 99.99% and 99.9999%. Comparably, a singularly hot universe made no prediction at all. 2. Equal temperatures and properties for the universe even in causally disconnected regions. A universe with a singular beginning made no such prediction. 3. A universe devoid of exotic high-energy relics like magnetic monopoles. An arbitrarily hot universe would possess them. 4. A universe seeded with small magnitude fluctuations that were almost but not perfectly scale invariant. A non-inflationary universe produces large magnitude fluctuations that conflict with such observations. 5. A universe where 100% of the fluctuations are adiabatic and 0% are an ISO curvature. A non-inflationary universe has no preference. 6. A universe with fluctuations on scales larger than the cosmic horizon. A universe originating solely from a hot Big Bang cannot have them. 7. And finally, a universe that reached a finite maximum temperature that's well below the Planck scale, as opposed to one whose maximum temperature reached all the way up to that energy scale. The first 3 points were postdictions of inflation, the latter 4 were predictions that had not yet been observed when they were made. On all of these accounts, the inflationary picture has succeeded in ways that the hot Big Bang without inflation has not. During inflation, the universe must have been devoid of matter and radiation and instead containing some sort of energy, whether inherent to space or as part of a field that didn't dilute as the universe expanded. This means that inflationary expansion, unlike matter and radiation, didn't follow a proper law that leads back to a singularity, but rather is exponential in character. One of the fascinating aspects about this is that something that increases exponentially, even if you extrapolate it back to arbitrarily early times, even to a time where t is greater than -0, it never reaches a singular beginning. Now, there are many reasons to believe that the inflationary state wasn't one that was eternal to the past, that there might have been a pre-inflationary state that gave rise to inflation, and that whatever that pre-inflationary state was, perhaps it did have a beginning. There are some theorems that have been proven and loopholes discovered to those theorems, some of which have been closed and some of which remain open, and this remains an active and an exciting area of research still today. But one thing is for certain, whether there was a singular ultimate beginning to all of existence or not, it no longer has anything to do with the hot Big Bang that describes our universe. The original definition of the Big Bang has now changed, just as our understanding of the universe has changed. If you're still behind, well, that's okay, the best time to catch up is always right now. Indeed, because more and more evidence is showing that the Big Bang wasn't really the beginning of it all. Earlier this year, NASA's time machine, the James Webb Space Telescope, finds evidence of massive galaxies that defy theories of the early universe. These galaxies, described in a new study based on Webb's first data released, are so far away that they appear only as a tiny reddish dot to the powerful telescope. By analyzing the light emitted by these galaxies, astronomers established that they were viewing them in our universe's infancy, only 500 to 700 million years after the Big Bang. Such early galaxies are not in themselves surprising. Astronomers expected that first star clusters sprung up shortly after the universe moved out of the so-called Dark Ages, the first 400 million years or so of its existence, when only a thick fog of hydrogen atoms permeated space. But the galaxies found in the Webb images appeared shockingly big. And the stars in them too old. The new findings are in conflict with existing ideas of how the universe looked and evolved in its early years and don't match early observations made by Webb's less powerful predecessor, the Hubble Space Telescope. We had specific expectations for the type of galaxies that live in the early universe. They are young and small, Joel Asia, assistant professor of astronomy and astrophysics at Penn State University and one of the authors of the study, told Space.com in an email. Previous studies of the early universe with Hubble and other instruments tend to find small blue baby galaxies at early times, objects that have just recently formed out of the primordial cosmic soup and are themselves building their early stars and structures. Young stars in general shine bright blue, with age stars develop a red or glow as they burn through their fuel and cool down. In ancient galaxies that Webb was built to spot, astronomers had not expected to see old red stars. They also had not expected to find galaxies more massive than perhaps a billion suns, but those reddish dots revealed in Webb's deep fields appear 50 times more massive than that. We're finding galaxy candidates as massive as our own galaxy when the universe was 3% its current age, Leisure said. Leisure also said that before astronomers start rewriting cosmology theories to explain how these galaxies came together so quickly after the Big Bang, they will have to ensure the odd red dots they are looking at are not something else. However, most of the alternative explanations also require entirely new concepts. For example, he said, stars in the early universe might have lit in exotic ways due to their lack of heavy elements, and perhaps we're not incorporating those in our models. Alternatively, perhaps our understanding of how stars form locally, for example, how many stars form from gas as a function of the mass of the stars, is totally inapplicable in the early universe. These things would also be exciting to discover and would also overturn our understanding of star formation in the early universe, just in a very different way, end quote. The images that revealed these puzzling galaxies were obtained by Webb's near-infrared camera, or NIRCam, as part of the Cosmic Evolution Early Release Science (SEWERS) program. Astronomers plan to soon turn Webb's mirror to these galaxies again, this time to obtain light spectra from those distant dots. Spectra break down the observed light according to its wavelength composition and thus reveal the chemical and physical properties of its source. The most important thing is that spectra give very precise distances to these objects, said Leisure. The distance and the identity of these objects are correlated. If we know the distance, we can pin down the identity, and vice versa. So a spectrum will pretty immediately tell us if our hypotheses are correct or not. Only a little more than 6 months after the Webb team released the first observations from the Grand Observatory, scientists are already challenged to rewrite their theories about the early universe. This is very exciting, as Leisure said in a Penn University statement. We looked into the very early universe for the first time and had no idea what we are going to find. It turns out we found something so unexpected it actually creates problems for science. It calls the whole picture of early galaxy formation into question. End quote. Well, that's all we have for you today. We hope you enjoyed today's episode. Thanks for watching, and we'll see you next time.